All right, let's get right into it. When we think about wind, we feel it moving sideways, right? A breeze on your face, a gust shaking the trees. But here's the thing. Its most important action, the part that really makes our weather, isn't horizontal at all. It's vertical. Today, we're going to look up and see how the wind we feel down here creates what happens miles above our heads. And we'll start with a question you've probably asked yourself every time you've watched a weather forecast. We all know the drill. A big L on the map is moving in, and that means, grab your umbrella. But why? What is it about low pressure that actually cooks up clouds and storms? Because if you really stop and think about it, it doesn't quite add up. Basic physics says air should rush from high pressure to low pressure to balance things out. So a low pressure system should just fill itself up and poof, disappear almost instantly. But it doesn't. And the secret to why it survives, and even gets stronger, is happening way, way above the ground. This little puzzle leads us to our first big idea, what we can call the cyclones paradox. And just so we're all on the same page, cyclone is just the official weather nerd term for any big low-pressure system. So what's actually going on at the surface when a low is nearby? Well, the key process is called horizontal convergence. Now, that sounds super technical, but it's really just a way of saying air is being pulled inward from all over, getting squeezed into a smaller and smaller space. Yeah, you can picture it just like this. The wind spirals in toward the center. It's a constant inflow of air at the surface. But hold on, this is where the paradox really hits. If you keep piling more and more air into one spot, what should happen? The pressure should go up, right? It should cancel itself out. And I absolutely love this analogy from our source material. A low-pressure system should just destroy itself, just like the sound you hear when you pop open a vacuum-sealed can of coffee. That psst sound, that's air from the outside rushing in to fill the vacuum. The low pressure is gone in a second. So why do storms last for days? Well, like we hinted before, the solution to this coffee can mystery isn't down here on the ground with us. Nope, the answer is aloft. To figure out what keeps a storm alive, we have to look up, way up. So here's the bottom line. For that storm system to keep chugging along, something else has to be going on up high. It's like there needs to be an escape valve to make up for all the air that's piling in down below. And this explains the whole machine. Think of it like a two-level engine. Step 1, down at the surface, air converges, it flows in. But step 2, this is the secret ingredient. Way up in the atmosphere, that air flows out. That's called divergence. So what happens to all the air caught in the middle? It has absolutely nowhere to go but up, and that upward rush is what powers the storm. Okay, so why is rising air the magic ingredient for bad weather? It all comes down to simple physics. As that column of air gets pulled upward, the pressure around it drops, so it expands and gets colder. It's just like when you use a can of compressed air and it gets chilly, right? Same idea. And when air gets cold, the invisible water vapor in it can't stay a gas anymore. It condenses into tiny liquid droplets, and boom, you've got a cloud. If there's enough moisture, you get rain. Simple as that. A great way to really make a concept stick is to flip it on its head and look at the opposite. We've seen how low pressure means rising air and storms. So what about a high pressure system? Well, as you've probably guessed, it's the exact reverse. We're talking fair skies. It's the same two-level engine, it's just running in reverse. And these high-pressure areas have a name too. They're called anticyclones. They're the sunny, calm weather counterpart to the stormy cyclone. And this table just lays it all out perfectly, side by side. For a cyclone or a low, you have air coming in at the surface and going out up high, which forces the air to rise. For an anticyclone, a high, it's the total opposite. Air comes in up top and flows out at the surface, which forces the air to sink. And that difference in vertical motion is everything when it comes to the weather you get. And here's why that sinking air matters so much. As it sinks, it gets squished. It's compressed. You know how a bicycle pump gets warm when you use it? Same thing. That compressed air heats up. And warm air is thirsty. It can hold way more moisture. So it basically just evaporates any clouds that might be trying to form, leading to those beautiful, clear blue skies. So what does all this mean for us down here on the ground? Well, this whole atmospheric dance is something we can actually keep track of. It's all about learning how to read the air. And this is exactly why that old-school barometer hanging on the wall actually works. It's not magic. It's measuring that surface-level pressure. So when you see the needle start to fall, it's a huge clue that a low-pressure system, our cyclone, is on its way, and air is about to start heading up. There's even a classic little rhyme that sums it all up so well. When the glass falls low, prepare for a blow. When it rises high, let all your kites fly. It's a perfect, simple guide based on everything we've just talked about. Falling pressure means rising air and storms. Rising pressure means sinking air and clear, kite-flying weather. And this brings us right back to where we started, the nightly news. The next time you see a weather map with those big blue H's and red L's, you'll know exactly what's going on. The meteorologist isn't just pointing at letters on a map. They're showing you where these giant, invisible weather engines are and where they're headed next. So it turns out the weather map only shows us half the story. The real driver, the thing making it all happen, is this incredible, invisible dance taking place miles above our heads. It really makes you wonder, doesn't it? What else are we missing by only looking at the surface?